Good morning, everyone. We completed the design of 4-bit adder with and the subtractor in the same circuitry. We completed the design implementation with the use of full adder and also with the use of one controlled inverter we utilized for the purpose of the addition and subtraction so that we can perform addition and subtraction in same circuitry. So any kind of doubt from the previous lecture? Anyone? No doubt. Okay, so we will start today parity generator. We know that in the last unit we have studied the utilization of parity code. What are the uses of the parity code for the error detection? Okay. Yes, okay. For the we know that if the data is coming from the transmitter adds append that data that append one bit into that data or whatever code is there. With that code, it transmitter append one bit. It depends on the it is utilizing the even parity code or the odd parity code. So this is just, it seems like it's a hypothetical thought, because whatever happens, whatever we are doing in theory, it there should be some kind of circuitry. We need some circuitry to do that thing. So here again, just the way we have designed implemented adder and subtractor, we also require some circuitry to generate that those particular parity bit for the combination of the bits. Depends on the data contains how many number of bits are there in that data. Okay, so we will start. We know that there are two types of parity: even parity and the odd parity. Okay, so data could be any number of data contains various number of bits actually, and actually multiple bits. The bit stream contains so many number of bits, but depends on what kind of technology transmitter is utilizing for the transmission of that data. So on the basis of that thing, number of bits will be decided for the transmitter through that transmitter medium. Okay, whether it could be because that, but those bit stream which contains the data, we divide that bit stream into certain packets. Okay, so that could be, the packet could contain 2-bit, 3-bit, 4-bit, and 5 bits, anything. Okay, suppose we'll start from the 2-bit. If the data contains 2-bit, okay, so if the data contains 2-bit, what will be the, how we will generate the parity bits for that 2-bit data. So we know that from the our previous knowledge, that if the data contains 2 bits A and B, so how many combinations will be there? What are the probable combination of these 2 bits? 4 combinations will be there. Okay, so 4 combination: 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so okay, you know the fundamental principle of parity. So we know that there are two parities, even parity and odd parity. So first we will consider the even parity. So it's now you have 1 minute. Try to find out the even parity, and because this is the truth table, because we don't have any boolean expression, or we know that if we have boolean expression, then we, on the basis of that boolean expression, we can find out the circuitry, the implementation we can done by the use of the various kinds of gates, with whatever gates we have already studied. We can use those gates for the implementation of that boolean expression. But again, we have only task that we need to generate the parity, but from the basic fundamental principle of parity. So we will form the truth table, and with the use of that truth table, we will try to find out the boolean expression for the even parity and odd parity. Try to find out the boolean expression for the even parity and odd parity. Now you have 1 minute to do so. Can you try? Yes or no? Jesse? Okay, try. Okay, so this is A XOR B, A X not B, right? Okay. So because you know so if you know the fundamental principle, you can implement any of the circuitry with the use of the truth table and with the use of the boolean expression. Okay, so this is very simple design, the generation of the parity bits. So from this here, this is the parity bits. So for this, if we say we want to know the even parity, so even parity for this we want zero, because input contains zero number of one, so it is even. So we don't want any one to be appended here. For the second combination, there is one, so here odd number of ones. So to make it even, we need to append one. Here again for the next combination 1 0, again here odd number of ones are here. So to make it even, so we need to append 1. So for the last combination, it is 1 1 and it is even, so we don't need any 1 to be added to, so this will be 0. So it's very simple. So just what we have to do, we need to solve the K map, and on the basis of the K map, it came out as XOR. Okay, so for these, it is 0. So A XOR B, and for the odd parity, it came out as A XOR B. Okay, so how to implement? Just a simple implementation for the, if we talk about the even parity, so the implementation is very simple here. which is simple XOR gate we can utilize here for the implementation of this even parity if the code is of 2 bits. If the code is of 2 bits, so it's very simple to generate the parity bits here. Okay. Just like even parity, we can also use the odd parity. Here, what we have to do, just the X nor is, we need the X nor for the odd parity for those same inputs. Okay. A dash B dash plus AB. Here, this is the odd parity. 0 0 0 0 parity is 1. 0 1, because already odd number of ones are here. We don't want here 1 to be appended. 0 1 0 odd number of ones are here, so parity will be 0 1 1 even number of ones. To make it odd, we need 1 to be appended. So here parity will be 1. So for that thing, 1 1. So if we try to find out, solve this K map, we get this A dash B dash plus A B. So simple implementation for this will be what? Only simple NOR gate, XNOR. Okay. So XNOR is just the complement of XOR. So if we have XOR and NOT gate, so after the XOR, if we use NOT gate, so it will be converted into XNOR. What about if the data contains 3 number of bits? So then what will be the minimized Boolean expression? This is also very easy. Only here if the 2 number of bits are there, 4 number of combination. If the number of bit, if the data contains 3 number of bits, then for even and odd parity, what we have to do, we need to we have to take 3 bits, and if the 3 bits are there, so the combinations will be 8. So we, for the 8 combination, we will try to make the truth table, and this is the truth table for the even parity 3-bit data code. Okay, truth table. We the fundamental principle is that you have to find out the Boolean expression whether it is already given, or if it is not given, then according to the task, try to find out the truth table, and in the basis of the truth table, try to solve the Boolean expression. Okay, so now for the 3-bit even parity, if we say we want to know the even parity, so the 8 combinations are here: 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. So here for the first combination, parity will be 0 0 0 1 because here odd even number of ones are here. For the next combination, it is odd number of ones are here. So to make it even, we need a 1. So here 1, parity bit will be 1. For the next, it is 0 1 0. Again, it is odd number of ones. So here we need to append 1. For the next combination, it is 0 1 1. So again here even number of ones are here, so we don't need the parity bit 1, so we need parity bit 0. For the next combination, it is 1 0 0 1 and so on. For the last combination, which is 1 1 1, odd number of ones are here, so to make it even we need to append 1, so parity bit will be 1. So according to this, we will try to see now for what combination parity is 1 and for what combination it is 0. So we will try to solve using the K map. So we have, this is the K map, and if we try to solve this, it came out as the C XOR A XOR B. Okay, so what we have to do, we just require 2 XOR gate. Okay, so for the 3-bit even parity, we require, this is 1 XOR for the 2 inputs. for next input, which has to be XOR with the remaining two inputs, will be this. Here it is not bubble. Okay, so this is C. So this is the 3-bit parity generator circuitry for 3-bit and this is for even parity. So like this, you can do you can solve this for the odd parity. Okay, so can you do for the odd parity for 3-bit? What will be the expression and how many what type of gates we need to implement the odd parity generator for 3-bit data. So okay, you try to do that. It's very easy because you know the truth table, how to make the truth table and how to minimize the how to get the minimized expression according to the truth table. So this is all this was all about parity generator for the 2-bit and the 3-bit. So next topic is multiplexer and the demultiplexer. Okay, what do you understand by multiplexer? Any idea about? Okay, no idea. Then we'll see. Sometimes it happens because what we do, we are what if in the digital circuitry or in the analog circuitry, what we are doing, we are playing with the data, actually stream of data or the some certain signal. Okay, so that whatever signal is there, signal or information is there, we are representing that information in terms of the stream of some bits, we because we are dealing with the with the digital electronic circuitry. So whatever data, signal or information is there, whether it is any kind of any document or any kind of information, so that what we need to transmit that data from the, so there will be two and entity will be there. One is the sender, one is the receiver. Okay, so whenever because and one more thing is that when the communication is going through some cable or wirelessly, there will be some uh, medium. Okay, so that medium could be the could be like copper wire, or if we talk about the long distance communication, so the air will be the or free space, actually the free space will be the medium. Okay, so there will be some conditions like multiple data are at the transmitter side. Okay, and for multiple number of data like 10, 12, 15, 16, any number of data. Okay, so those for those multiple number of data, whenever we design any of the circuitry, we have some constraint about the hardware complexity, about the area. So when multiple number of data, multiple number of sources are there. Okay, so and one is the transmit at the one is the receiver. So those data will be transmitted through one medium. So it is not possible to implement that medium for each and every sources. So what we have to do, we have to use a single medium. Depends on what depends on the condition. It depends on certain condition. So here what the you here for that thing to happen, because we have some hardware complexity, we have some constraint from about the area. So because if we use the medium as the wire, so multiple wires we need if multiple sources are there. So to reduce the that wired complexity, so we use the multiplexer. So multiplexer is just a circuitry which takes multiple number of data and select one data among those multiple number of data, okay, from the multiple sources. So this is also, multiplexer is also called as a data selector or many to one selector. So this is the multiplexer. So when you study microprocessor or any other circuitry, so you will notice that what is multiplexing. So here this is the fundamental principle of that multiplexing. There are different schemes are there. So according to those schemes, the data is selected on the basis of the conditions. So here those conditions are called as the selection lines. Which data will be selected among those multiple number of lines, it depends on the condition, and here in the digital circuitry that condition is decided by the some particular number of selection lines. So suppose the data is of 2 to the power n number of data is there, okay. So and 2 to the power n is equal to, suppose it is m number of inputs or m number of sources are there. So what will happen, how we decide the selection line, it depends on what is n. So n is equal to number of selection line, okay. So now n is equal to number of selection line. So it directs one of the input from those multiple number of inputs towards one output. So it contains, so the basically microprocessor contains various number of inputs, some combination of the selection lines and one output. So this is the multiplexer, and the short form we call this multiplexer as the MUX. Here the simple thing is that what happens, so we have different devices like some MP3 player, laptop, digital satellite, digital cable. So and this sound system, we need to direct one of the input towards this sound system. So on the basis of, so this is the symbol, actually this is the symbol of the multiplexer. So here we have 4 number of inputs. So for the 4 number of inputs, it will be 2 to the power 2 is equal to 4. So how many number of selections line we need? We need 2 number of selection lines to select one of the input for among those four inputs, okay. So one multiplexer, with the use of the multiplexer on the basis of the various combinations of the selection line, one of the input will be directed towards that sound system. So multiple number of sources are there. This selector is, we can take that selector as a multiplexer, and that will be directed towards that whatever receiver device is there. So these are the transmitting device, this is the selection device, and this is the receiving device. So this is the multiplexer. So the simple block diagram of the multiplexer is like this. We have some data inputs. It could be any number of lines, and number of lines are there. So n is equal to 2 to the power x is in n. So x will be the selection lines, okay. If n number of lines are there as an input and 2 to the power x is equal to n, here x will be selection lines. And the symbol is, we can, whenever you see symbol like this, so we can say that this is what is the function of the circuitry. It will provide the multiplexing. So this is multiplexer. This is for 4 inputs. So for 2 input, for 8 input, for 16 input, for 32 input, we can make the multiplexer. So now what is inside, we need to see what is inside this block this symbol, okay. So we need to find out what is inside this block, because there has to be something like the combination of certain gates, basic gates or whatever gates we have studied. It should be the combination of those gates. So how we will form those combinations? So actually the multiplexer could be like 2 to 1, 4 to 1, 8 to 1, 16 to 1, or 30 to 1. It could be anything. So we'll take some fundamental multiplexer like 2 to 1, 4 to 1, 8 to 1. Okay. So what do you understand by 2 to 1? 2 to 1, it means number of inputs will be 2. Okay. So in the power of 2, it is 2. So how many number of selections line will be? Selection lines will be 1. Okay. So for this selection line, so suppose if I0, I1 are the inputs, so selection line is this one and output is this. So we have to find out how to implement this circuitry. So this is selection line. Because only one selection line is here, so how many combinations are there? Only two combinations, and also we have only two inputs. So if selection line is 0, it means I0 will be selected. If selection line is 1, then I1 will be selected. Okay, so this is just a truth table. So we will understand with the use of some bigger multiplexer. Okay, so very simple, it will be very easy to implement. We'll see with the use with the example of 4 cross 1 or 4 to 1. So here for the 4 to 1, suppose I0, I1, I2 and I3 are the input lines, 4 input lines. So how many number of selection line we need to select among those one of the lines? How many number of selection line we require? N equals to 2. Okay, so selection lines will be 2. Okay, so these are the selection line S0, S1, Y. Combinations will be 4 combination and also 4 number of inputs. So 0, 0, 0, 1, 1, 0, 1, 1. So if 0, 0 is there, I0 will be selected. If 1, 0, 1 is there, I1 will be selected. If 1, 0 is there, I2 will be selected. And if 1, 1 is there, I3 will be selected. Okay, so now we have to find out what will be the, how to implement this thing. So here, this is the thing. Okay. Okay, this is C0, C0, C1, C2, C3, because inputs are C0, C1, C2, C3. Okay, so here the elaborated truth table will be like this. Here S1. So we know that if combination 0, 0 is selected, what will if combination S0, S1 is if the combination of S0, S1 is 0, 0, C0 will be selected. So here whatever value of C1, C2 is there, we don't care about this thing. Okay, so if C0 is 0, here output will be 0. If C0 is 1, output 1 will be selected. For the next combination for 0, 1, we noted that what will be selected? C1 is selected. So whatever value of C0, C2, C3 is there, we don't care about those values because on the basis of the combination of the selection line. C1 is selected, so if the C1 is 0, it output will be 1. Output will be 0. If the C1 is 1, output will be 1. If for the next combination it is 1 0, C2 is selected, so here 1 0 is here. So if whatever value of C0, C1, C3 is there, we don't care. So if C2 is 0, output is 0, C1 is 1, output will be 1. And for the next combination 1 1 of the selection line, C3 is selected, so whatever value of C0, C1, C2 is there, we don't care, only we are interested in C3. So if C3 is 0, output is 0. If C1 is 1, output is 1. So to obtain the Boolean expression, what will be the Boolean expression? Suppose, so here the Boolean expression will be like this, because output, we want the output to be selected when the combination of appropriate combination of the selection line is there. Okay, so S0 dash S1 dash C0, okay, plus C1. Okay, so here combination is S0 and 1. So 0, for 0 it will be S0 dash S1 C1 plus, for C2 combination is 1 0, it means S0 S1 dash plus, for the next input it is 1 1, and which will be S0 S1 C3. Okay, so now tell me what we require here. So what will be the circuitry to form to implement this expression for the 4 cross 1 marks or 4 to 1 marks? What we need the one AND gate, 3 input AND gate. This is 1, this is C2. 1 2 3 4 4 3 input and gate. Okay, 3 input and gate, and 1 4 input or gate. So with the use of the 4 3 input AND gate and 1 4 input OR gate, we can implement this 4 cross 1 marks. Now one more thing is that we also require NOT gate. Okay, so we require some NOT gate. So how we will implement? This is the implementation. Okay, so the combination is this. So here we require NOT gate for the complement of this S0 and S1. Okay, so this is we have concluded that here we have how many number of 4 3 input 4 3 input AND gate and 1 4 input OR gate. Okay, so here this is the first which is for the S0 dash S1 dash, and this one is for S0 S1 dash, this one for S0 dash S1. Okay, then this one for S0 S1. Okay, so and this is the ORing of all those things. So try to find out how if it is working or not. So suppose for S0 dash S1 dash. So suppose the combination is, if the selection line combination is 0 0. So now we will see the output. We know that our output is what? Here output is this one, S0 dash S1 dash C0 plus S0 dash S1 C1 plus S0 dash S1 C2 plus S0 S1 C3. This is the combination. Okay, so for the if the combination is, suppose the selection line is 0 0, so we'll see S0 dash S1 dash will be 1 1. So the output of this first and gate will be what? 0. So now we see, if we see that what will be the output of remaining gates. So here, so if we notice for selection line 0 0, this output of this gate will be 0, for because if 0 0 is there, so here S0 will be 0, so multiplication, the ending is 0. So here again, if we check this one, it will be 0. If we check this one, this will also 0. So here the input of the, if we see the OR gate, so 4 inputs are here. So among those 4 inputs, only one input is 1. So 1, it will become 0 1 0 0 and 0. So output will be 1. Output will be, it's not 1, it will be C0 actually, because it is 0 0. The output of this first AND gate is C0. So output Y will be C0. Next, let's see for the combination. If the combination is 0 1 1 0, okay. If the combination is 1 1, if the combination is 1 0, if the combination is 1 0, so try to find out what will be the output. Okay, so in this example, this is the expression. Okay, and 1 0 is there. So okay, S0 S1 1 0. Okay, so here for this, what will be the value? Here S0 dash S1 dash C0. So it will be 0. Okay. For this one, what will be the value? Here S0 dash and S1 is going inside and C1. So again it is 0. For this one, what is going? S0 and S1 dash C2. So again values of these things will be 1. So here the output of third gate will be C2. What about the fourth one? The input is S0 S1 C3. So for this S0 S1 is 0 combination, so C3 ending with C3. So here it is 0. So the inputs will be what? Of the OR gate is 0 0 C2 and 0. So the output will be what? 0 plus 0 plus C2 plus 0, and the output will be C2. If the combination is 1 1, we can check here. If the combination is 1 1, so we can observe, we can see that. Everyone please put your scholar number into the chat box. 1 1. Okay, so for the 1 1 combination, it is See, it will be 0, this will be 0, this will be 0, this will be 1. So what will be the output? 0, 0, 0. It's not 1, it will be C3. 1 will be the S0, S1 is 1, and which is ending with C3. So these values will be 1 and it will ending with C3, so it will be C3. So here 0, 0, C3. So this is 0. So the output will be 0 plus 0 plus 0 plus C3. So this is the 4 cross 1 or 4 to 1 multiplexer implementation with the use of different gates. Okay, so this is the implementation using 4 cross 1 implementation of 4 cross 1 mux. So what about the 8 cross 1 mux? For the 8 cross 1 mux, how many number of selection lines we need? 3. Okay. So we need 3 selection lines. So how many combination we need? We require 8 combination of those selection lines. So 8 because 8 number of inputs are there. So 8 combinations will be there. So the Boolean the expression will be again same way we'll try to find out. So the combinations are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1 and up to 1, 1, 1. So if the selection lines values are 0, 0, 0, so the output will be D0. If 0, 0, 1, it will be D1. If 0, 1, 0, it will be D2. 0, 1, 1, it will be output will be D3. Because D0 to D7, we assume that these are the 8 input of this 8 cross 1 or 8 to 1 multiplexer or mux. So here for the 1, 1, 1 combination, the output will be D7. So for the implementation, what we have to do, just we need to take again the way what we have done in the 4 cross 1, we will follow the same procedure. So S0 dash, S1 dash, S2 dash, D0 plus S0 dash, S1 dash, S2 D1 plus S0 dash, S1, S2 dash, D2 plus S0 dash, S1, S2, D3 plus S0, S1 dash, S2 dash, D4 plus S0, S1 dash, S2, D5 plus S0, S1, S2 dash, D6 plus last expression will be S0, S1, S2 and this is D6. It will be D7. So this will be the expression for 8 cross 1. Can you implement this with the use of the gates? Yes, it is possible. How many number of and what kind of gates we require here? What kind of gates we need? Tell me. Same gates. If you, yes, four input, 8 AND gates, and yes, 8 input OR gate. 8 input OR gate, 4 input AND gate, and 3 NOT gate. 3 NOT gate, okay? So this is okay. So this is the implementation of the 8x1 mux with the use of AND, OR, and NOT gate. So this is the simple implementation. Here it will this generate this is for the combination 0 0 0 combination. It generate this is for 0 0 1 combination. This is for 0 1 0, for 0 1 1, for 1 0 0, and so on, and 1 1 1. So on the basis of the values of the selection line, it directs the input towards the output. Okay. So any doubt till now? Anyone? Any kind of doubt? No? Okay. So in the next lecture, we will see the what is a demultiplexer, and one more thing is that how to implement in the previous in the last unit what we have what we did, we just use the various gates to implement the Boolean expression. Now here, after studying the multiplexer, we will try to implement any kind of Boolean expression with the use of the multiplexer. There is a possibility to implement any kind of Boolean expression with the use of multiplexer too. So in the next lecture, we will see demultiplexer, various kind of demultiplexer, and the implementation of Boolean expression with the use of multiplexer too. Okay.